Not yet. Yeah, now we can see.
Now you can see, right? Yeah, that. Thanks for confirmation. And let me hide the video panel so that it could easy for you all. Take this participants right side. Yeah. Okay. Mm-hmm. Yeah. Dun, 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 dun. Can anyone recall it what we had discussions are happened in the last week? Anybody? Just I need some kind of overview from anybody. Uday, can you take over that thing? Like, could you explain what we had discussion, what we had discussed in the last week?
Yes, sir.
Yeah, go ahead.
Yeah, we have thought about the deep learning architecture,
Hmm?
and we have thought about the practical applications and how deep learning raised from
Mm-hmm.
past years,
Mm-hmm.
and the input layers, hidden layers, and output layers, and the
Mm-hmm.
terminology we use in that architecture.
Okay.
Yeah, till there we have learned, and you told us we'll continue by telling about convolution and rest of the things.
Those things, yeah, those things we'll discuss after this complete understanding of neural network, okay, or else deep learning part. I hope you can see the image on my screen if I'm wrong, right? See, this is exactly the architecture of neural network. Try to understand here. So here we have various inputs. This is input one, input two, input three, and input four. These are the inputs. Okay, so we are assigning random weights for each and every input. Okay, so this input it is having its one weight. Okay, and this particular input is also it have its own weight, random weight. First of all, we try to understand it's a kind of random weight. So this input is also having one more random weight. So this input is also having one more random weight. Now what we are doing actually, this input and this weight, we are feeding to the input for the one neuron. Same input and same weight, we are feeding to the input for the another neuron. Okay, this is the way the entire is all neurons. We can simply say that it's a one layer. So this all neurons, which is not visible, which is not visible for us, that is the reason we can say it's a hidden layers. The hidden layer, which is consisting of a multiple neurons. These neurons will take the input from the previous neuron output as well as and the weight. The weight it could help you to carry your input from one neuron to another neuron. Hope you understood. What is the use of the weight, right? The use of the weight is to carry your input from one neuron, one output, the output value of one specific neuron, which could be input for someone, right? Okay. So that output, it has to feed to the input for a neuron that it is done by the with the help of the weight only. So this is how the neuron will take the input and weight, and it can do some kind of operation, and it can produce some output. That output will be again input for the another neuron. That is how at last we are getting some kind of output at that layer. Whatever we have it, that layer we can call it as the output layer. The first layer, what we have it, that we can call it as the input layer. In between input layer and output layer, we may have the n number of hidden layers. As of now, we can see here only one layer, but you can have multiple layers also. Okay, is it clear? And how many number of layers you want to be keep it your network? It's up to your choice. And how many neurons you want to keep in each layer? That is also your choice. And what kind of things will happening inside of the neuron, that we are going to be understanding now. I hope you understood, right? This is overall architecture. Within that one, we have various neurons are there. You need to understand what exactly the neuron is doing. If you understood really, then you can easily understood the entire network. Okay, but if you agree, then I can move forward. If not, then I can stay
No, no,
here
that's
and I
good.
can write. Yeah. Okay, cool enough. Now, okay. mm, okay. Now we'll try to understand what could be happening inside of the neuron, or what will do, um, what exactly the neuron will do. That we are going to be understanding now. Okay. So let me let me do one thing. And yeah, the activation function inputs BIOS. Okay. Yeah. Let me show you one more image for you all, and just take, this is the neuron. This circle, what you can see, this is the one individual neuron I picked up from the architecture. Okay. Something like this only. We have when you make it all neurons in one layer, that is one hidden layer actually. Okay. So each network or each neuron will do the same task. Okay, so for example, within the hidden layer, if you define that neuron could do this kind of thing, every neuron will do the same thing only. Okay, so try to understand what exactly the neuron will work. See, let me, yes, see here we have inputs, right? This input, which is carrying the weight also. This input and weight will feed, this input and weight will feeding to this particular neuron. And something like this, if we have n number of inputs, then each input it have its own weights. And at the first step, which is a simple linear regression, you carefully observe here, which is something like linear regression equation or not. Is it linear regression equation or not? Y equal to mx plus c. Yes or no? Y equal to mx plus c. Is it very similar to the simple linear regression or not? Okay. Yes or no? I need your confirmation. So this is a linear equation formula.
Oh, sorry,
Y
I was
equal
on
to,
mute. Yeah, yeah, that's right, that's right. It's
this
simple
is y.
equation.
Yeah,
Yeah.
it's a simple linear equation. So here, what we are doing actually, we are taking inputs and weights, and we are summing, we are multiplying the input and weight, and how many inputs we have it, we are summing those things actually, and we are adding at last one bias also. Okay, optionally we are going to be adding the bias. So this is the B is a bias, and sum of the weights and inputs plus bias, which is a linear equation. So this is the step number one. In step number one, which is simply a linear equation. Okay. And in step number two, this linear equation, and see what happen if you keep only this linear equation in this particular entire neural network. Oh God. Okay. I'm not add any kind of, I didn't add any kind of activation function. Uh I just following that, some of the weights and those inputs only. Okay. That particular situation, each neuron, which is the linear equation only, which is having only linear equation only. So you will get a number, right? Okay, it may be a number. Always we are getting a number. So this entire network, it can be a linear nature. Okay, but if your entire network, which is in a linear nature, it won't learn things, it won't learn the complex patterns. Our aim is what? Whatever the data we have it, whatever the data we have it, okay, whatever the data we have it, it is a bit complex because which is having a n number of inputs, and it have a lot of deep information we have it to understand the sub patterns as well. So linear nature, it won't work well. So that is the reason what we have to do to this particular linear equation, we have to apply the non-linear nature. That is where we are going to be doing the activation function. Clear?
Mm-hmm.
Okay. So let's do now what we are doing exactly. Uh, if all neurons is having only linear equation, then output is also it could be linear, right? But all scenarios, maybe you're in real world, everything which is in a linear nature. So many things have a non-linear nature also, right? Okay. So definitely your deep learning never work actually. So that is the reason for your linear equation. If you are applying the activation function, then it can able to adding some kind of non-linear nature to your linear equation. That exactly the activation function is doing. So, and which is giving, it is producing some output is also with help of this activation function, which is producing some output. And we do have various activation functions are there. And finally, we are getting some kind of output here. The output name is A here. Okay. So try to understand this particular circle, that is neuron, the neuron which is having inputs and weights. And initial step, we are summing and multiplying and weighted sum of inputs and weights plus bias also. And this entire equation we are feeding to the activation function, and the activation function producing some kind of output. So what exactly the activation function is doing, let me explain now. So just 1 second.
No, the function of z, that linear equation itself is the function, right?
Linear
The
equation.
neuron itself is calculating with an activation function which is f of z, means
Yeah.
the function of z, that entire equation.
Mhm. Yeah, so that's what that neuron I'm expanding into something like this, and hopefully you can easily understood. See, for example,
Mhm.
yeah, see. Mm. Okay. See, these are the inputs, right? And weights, right? In this is the first step. And this is linear equation. Linear equation is not the activation function. It's a linear equation. We are weighted sum of inputs and weights and bias. Okay, this is the step number one. This this entire equation we are feeding to the activation function. So within this particular activation, this step is common for all neurons. This step is common for, even you can apply any kind of activation function. It's up to you what activation function you want to apply as per your requirements. But the first step, whatever we have it, that it could be the common for all activation function. Okay, till it won't
All
change.
activation functions are all neurons.
All neurons as well as all activation functions also.
So the input to the activation functions will be same in all
Yes,
neurons.
the process is same, the value is not same.
Yeah, value will not be same because value will be defined based upon the input and
Yep.
weightage. That is
Yep.
okay.
Yeah.
So the process calculation is same across
Yeah.
all neurons, and that
Yes.
input we are
Yes.
giving to the activation function.
Yes, yes. You can see whatever the step you can see in left side, this particular
Mhm.
step, it could be common for all neurons. And it could be common
Okay.
for all neurons as well as you can apply any activation function. This step is common. Within the neuron, you can apply any activation function. This step is common. And for all neurons, this step is also common. Okay. Only the thing what we are changing, only the name, only the activation function strategy we are changing in different applications or different requirements. Okay.
Mm.
Yep. Mm. Any confusion over here? See,
Yeah, not exactly convinced with that architecture diagram of the hidden layers. If we just go back, or if we can we keep this diagram and the previous architecture input and yeah. So now the hidden layer. So the input layer will not have the activation function, or will that have an activation function?
no
So
input
every
layer.
new every neuron in a neural network architecture
Mm,
will be defined with the inputs and the activation function, right?
yeah.
Okay. So every neuron in that layer.
Only
Okay.
input layer. It doesn't have any activation function. Only input
Yeah,
layer.
exactly. So
It
only
doesn't
hidden
have
layers, only hidden layer neural network, sorry, hidden layer
output
neurons,
layer. Mm,
yeah,
mm.
will have these activation functions. Okay.
Yes, yes, yes. See, in this architecture, we have three layers: input layer,
Mm-hmm.
output layer, hidden layers. Okay.
Yeah.
the name output layer is output layer, but output layer is also one kind of hidden layer only. Okay, but the hidden layer which is in the last stage, that is the reason we are calling it output layer.
Okay.
Okay, so this is also one kind of hidden layer only. This is also one kind
Yeah.
of hidden layer only. Only this is a thing is not hidden layer because it doesn't have any neurons, which is having only inputs and assigning some random weights, and that's it.
So
But
that
rest of
neuron
all,
doesn't do any perform
yeah,
calculations.
yes, it won't perform any calculation. Just for understanding, that could be one circle, but it is not the neuron. Okay, it just input
Uh,
value. Okay, input layer, there is no neurons. Input layer, we have only inputs. This inputs passing to neurons in the next layer with help of some weights also. This weights we are going to be assigning with our own. And this all are neurons only. Even output layer is also having the neuron only. And in
mm,
between input layer and output layer also we have multiple hidden layers, that all hidden layers also having the neurons only. The neuron, every neuron will performing two tasks. One is weighted sum, one is weighted sum, second one is applying the activation function on weighted sum. Okay,
mm,
every neuron with performing the two tasks. One is weighted sum of inputs and bias. Second one is the result of this particular weighted sum and bias given to activation function. This activation function can producing some kind of output. That output, it could be input for the next neuron.
okay.
Inside of the neuron, it can performing the two operations. Operation one is making the data as a linear nature. Operation two, applying nonlinear nature on top of the linear data. That's simple for more understanding. How you are applying
Okay.
the nonlinear nature to your linear nature with help of activation function.
Mm.
Okay. Yeah. Okay. So these are the different images. You can definitely helpful a lot. Let me, let me. Okay. Any further questions on top of this thing?
Nothing from my end.
Anybody? Did you understood what exactly the neuron is doing? But inside of the neuron, the only confusion is that we can use activation functions. I said we can use activation functions in second stage. We can have different kind of activation functions. We need to understand at what kind of situations which activation function we need to apply it. If you know that one, then you can create any architecture based upon your problem statement. Okay. For example, you want to build the classification problem, and you want to solve the classification problem, then we can use the different activation functions. And if you want to solve the linear regression problems or regression kind of problems, then we have to apply the different activation functions. We cannot apply the same activation function for all kind of problems. Only the only thing is we need to always change activation function as per your problem statements. Okay, so in we do have a different kind of activation functions are there. Let's talk about each and every activation function, at what kind of situations we can apply and what kind of problems we can face on with the help of those particular activation function. If, for example, if you apply one particular activation function, what kind of Done? You can see, right? Hello?
Yeah, now we can see.
Okay. So what I'm trying to tell you, in neural network, without activation function, it's just a simple linear regression, no matter how many layers we have it. Okay.
Mm-hmm.
So that we don't apply the if we don't apply the activation function and on our layers, then finally it is also still it's a linear. No, learning of complex patterns. That is where activation functions are required to introducing some kind of non-linearity, and so that networks to learn the complex patterns, and it could help you to enabling some kind of deep networks to work on all. So let's go ahead with one by one. Let's start with the um, different activation functions, right? Let's start with the sigmoid function. Sigmoid is one kind of activation function. What is the first one?
Sigmod.
Yeah, sigmoid. Sigmoid is very basic and base kind of activation function. Everyone know it in industry. You can go even first year or second year student or employee. I mean, 2 years of experience employee also. If you ask any question, do you know about sigmoid function? Definitely you know it actually. That is a base kind of activation function. Okay, what exactly the activation function is doing? And see the formula, it is kind of exponential formula. Let me show you the formula, how the sigmoid activation function will have it. Okay, so you can see, right? This is the your sigmoid activation function formula. Okay, see what exactly happening here. Whatever input weighted sum we have it, right? Let me consider this x is not x. Can we consider z? Because in neuron, we have two steps. In step number one, we are calculating the jet, and in step number two, we are applying the activation function on top of the jet. Am I right?
Yeah.
Yeah. So how do you calculate the jet? It is having various inputs and output weights. For example, this is my x1 and this is my x2. And each input which having its own weights, random weights, and it is having a bias also. Am I right? Okay, we are sending the bias also, because neuron has to be learn something even if all inputs are zeros. If you are not receiving any inputs, at least the neuron has to learn something. I didn't receive anything. Okay, yes or no? So for that
Yeah.
one, we need to pass the BIOS also. So in JED, we are calculating the weighted sum, right? So that x1 w1 plus x2 w2, okay, and BIOS. Okay, we are BIOS also we are adding this entire equation. We are applying 1 by 1 plus e power of z. Okay, e power of minus z. Minus z means this entire equation or this entire value we are giving to a 1 by 1 plus e power of minus z. You will get some kind of values. The values, it could be between the 0 to what? 0 to 1. Okay, you will, you can pass any value. You can pass any z value. You pass negative values, positive values, infinity values, positive infinity values, zero value. You can pass anything. Okay, you can pass any value, but the value of this sigmoid function between 0 to 1 only. Clear?
Mm-hmm.
The range of output is, it is 0 and 0 to 1. So if something which is less than the uh, 0 0.5, that belongs to the 0. And if something is more than the 0 0.5, that we can make it as the 1 actually. So that is where it could help you to solving the binary classification problem. Okay. So simply I would try to confirm you, like output range is output range is output range is 0 0 to 1, right? I said 0 to 1, right? Okay. And if something is less than the 0 0.5, that is 0. It is treating as the 0. And if something is more than the threshold value, that is 0 0.5, that we can considering as the 1. Because of that one, it could help you to solving the binary classification problem, because you will get only two things, right? Either 0 or 1. That is the reason it could help you. When you want to classify something in a binary format, then we can use the sigmoid function. For example, I can give you a problem statement for you. You got a one mail. You got one mail, and we have a content something like this. And could you transfer $25,000 so that in the next 10 days you will get the $1 lakh, or you just transfer the 25 $250, then you will get the $1 lakh in next 1 month. Could you believe it? Is it like in a spam or not?
Yeah, that's
Definitely, because initial days we don't know. For example, if he's just having only 15 years, okay, he started using of emails or internet. Very he very short period of time he have some kind of experience on internet. Okay, he receiving this kind of mails. He definitely believe it, right? Okay, if I transfer $250, then I can get the 1 lakh in next 1 month. Then definitely can transfer the $250, and he may scam. He may get scammed actually. He don't know initially, but after one or two things are happening in his case or his friend cases, then he believe it. Okay, this is a fraud kind of mail, so I don't transfer any kind of amount to anybody. This kind of conclusion he will come out of it, right? So there we have two options, whether the received mail is spam mail or not. Because as a human being, we already seen some emails, or we already seen some kind of real time examples around surroundings of you or your friends cases or your cases, or or internet or different things. We learn it, this is the fraud email. Okay, in the same way, what we are doing actually, we are feeding the different kind of emails to your deep learning, and we are segregating some of the emails are spam mails and some of the mails are not spam mails. And the deep learning which automatically classify with help of this particular sigmoid functions, and this sigmoid function we can use it at output layer, and you will get either 0 or 1. If the output layer, if it is which is producing the 0, which means that the mail which is not spam. Okay, for example, the output layer which is producing or generating the 1, then it could be the spam mail. If you're feeding or if you're giving input is your email, and you will get output is the 0 or 1. So that kind of problem statements we can solve it with help of this particular sigmoid function. Is it clear?
Mm-hmm.
Yeah. Any other questions? And the problem is that when we are applying or sigmoid function, and you will get some of interview very important interview questions. The first one is vanishing gradient problem, and slow convergency, and not zero center, and so we do have some kind of mm, mm, problem here, because in between 0 and 1, 0 is center. No, right? It's not 0 center. It's not 0 center. Okay. And moreover, when you are applying this sigmoid functions, maybe your network, it will learn slowly. It won't learn instantly, or it won't learn a speeder manner. It can learn very slow manner. Okay, that is where we are getting some kind of problems, vanishing gradient problem. And so this names we can remember it. Which problem? Vanishing gradient problem. Those things I can explain you in the further sessions as well. Okay, vanishing gradient problem. Whenever I explain, when I would like to explain about optimizers and all, that back propagation, that time I definitely explain about vanishing gradient problem. You may get vanishing gradient problem when you are applying these sigmoid functions on top of your neurons. Okay. Yeah, how you can solve it, that we can definitely learn it, because of it's not centered towards to the 0, right? It's not 0 is not our centered value, right? That is the reason maybe it will take a lot of time. The output is simply, it's a binary classification. It is not recommended for hidden layers. See, uh, this sigmoid function, we we use at output layer, don't use in hidden layers. Are you getting my point? So you can use sigmoid function at output layers. don't use in hidden layers. Why? Because which will learn very slowly and which is generating non-zero centered values. So that is where we are getting vanishing gradient problem. That is where the model or the network, it will learn very slowly. Okay, that is the reason don't use sigmoid functions at hidden layers. We can use sigmoid function at output layer, especially when we have binary kind of classification problems. When you want to solve the binary classification problems, that particular situation, we can use the sigmoid function at output layer. What if we have multiple, what if we have multiple multi-class classification problem? So you are not having only binary classification. There might be chance of low, medium, high. There is a three classes are there, three categories are there. Then is it whether sigmoid function will work for us? No, right? If you have more than two classes in your data, is it possible? Is it useful for us? No, definitely no, because which could be classifying only between 0 and 1 only. So it cannot be classify multiple classes. So that is where we can apply the softmax. Which max? Tell me, guys.
Softmax, yeah.
Softmax. What is the use of the softmax? Softmax will help you to classifying the not for binary classification problem. It could help you to classify the multi-class. When your data is having multiple classes and you want to classify the multi-classification problems, or you want to solve the multi-classification problems, instead of using the sigmoid as an output layer, we can use the softmax as output layer in an output layer. Okay.
Yeah.
That okay. Let's see how the softmax will looks like. I hope sigmoid function you understood, right? The equation you understood, right? The equation, this is an equation, and these are the problems we might be getting, and it could help you only for binary classification. What if we have the multi classification, then again we are facing an issue. So that is the reason what we do, actually we do have with the um, submax function or multi classification layer. Okay, so here. Okay. Okay, see, you can observe here, this is output vectors. We are getting this kind of vectors actually. So this is your output layer, the output layer which is produced. Okay, so this is your softmax function. Okay, this is your softmax function. This is your vectors z1, z2, z3, z4. This is your vectors. Okay, I mean, before output layer also we have various hidden neurons are there, right? Each hidden neuron, it can be producing some kind of output, right? And that output and the weight, we are doing some, weighted sum and all, right? Okay, those vectors, those are vectors of each neuron. Okay, so this particular values we are applying on top of this particular softmax function. We are getting, these are the classifications. Okay, 0.02, 0.91, 0.06, 0.01. Okay, these are the different kind of probabilities we can able to get it out it, and this is the classification probabilities. Okay, so if any problems will comes under this particular um, ranges, then it could be this kind of classes. So this is the softmax activation function. Previously 1 by 1 plus e power of minus z, which is the, what is that? Which is the softmax, which is the sigmoid. But e power of z I by, if we have four classes, then I value is a 4 or j value is a 4. Okay, I mean k is number of classes. If you have four classes, then you can have the four vectors here. If you have the five classes, you will get the input is the five inputs actually. Okay, so that is how we have to feed these particular values to this particular function. It can be producing this kind of probabilities, and if the probabilities are belongs to this particular thing, then that those are the different classes we can assign it actually. This is how the softmax function will works well. Clear? Any questions? Any questions?
No for no.
Okay, how the softmax will works, right? So here also we have one mathematical formula. This is the formula. Backend of the softmax will works. I can will create this all kind of stuff practically. Don't worry, using Python
Oh,
program. Hmm? And but we don't need to create actuals. We don't need to create automatically in Keras or PyTorch libraries. If you just give the name automatically, which can be assigning these particular functions, but we can create our own way also.
okay.
Right. Excuse me. This is one example. Especially when we have multiple neurons, then we can use this particular thing actually. Okay, so multi-classification kind of problems, the time we can use this particular softmax function. I hope try to understand the names softmax sigmoid. Sigmoid is for binary classification. Softmax for the multi-classification. Okay, then at least you need to remember those things. When to apply it, if you know it, then that is fair enough. Even the softmax also, generally we are going to be using at output layer, not in a hidden layer. Okay.
Okay.
Yeah. So now we have a few more activation functions which are very, very important because this softmax and the sigmoid function which are not centered, zero centered. That is the reason we are applying we are going to be mm, tanh function, tanh activation function, which is improvement of sigmoid activation function. Okay. What is the name of the function is?
10H.
tanh. tanh. These names we need to keep remember it, guys. tanh activation function. So this tanh activation function, which is extension of your sigmoid function, and the formula is Windows Shift S. Okay, the formula is hmm, the formulas very easy formulas. You don't need to remember it, but no, I would like to show you, right. Okay, see, e power of x. This x is just simply z. Can keep understand this x is not x. It's z. I mean, the neuron step one result. The neuron which is performing two operations, right? The neuron which is performing two operations, right? The operation one, which is the z value. This is a z only. We have to keep it over here. Okay. And so this is where if you apply this z on top of this particular equations, then you will able to get the results are -1 to +1, -1 to +1. I would like to show you the graph of the sigmoid function for easy understanding, to remember easy manner. So let me show you. Okay, copy that. Okay, yeah. So I would like to show you just 1 second. Mhm. Okay, you can see this one. Um, you can see this one sigmoid. This color is there, right? So the value between 0 to 1 only. Okay, and but when you're applying the tanh, you will the output is it may producing -1 to +1, which is center of the 0. So this is exactly tanh activation function result values. If you plot it or the distribution of the tanh values, you will get this kind of a curve. If you distribute the sigmoid activation results, then you will get this kind of graph actually. Okay, so this is the small differentiation between the tanh and sigmoid. So the use of this particular tanh, the use of this one is the advantages
No,
is
but the
it is
tanh ranges from 0 to it's
tanh
not
is
for the,
minus 1 to plus 1.
that means we can understand like it is multi-class
No,
classification
no,
purpose we
it's
can
not.
do.
It's no, it's not multi-class. It is a for binary class only. If something is less than the zero, then it could be one class. Okay, something is more than zero, then it could be the class one, something like this. And which is not
Okay.
for classification problems actually, because sigmoid function and softmax function, which is producing some probabilities between the zeros and ones, it may not learn the things and all because which also having some kind of linear nature only. Okay, but when
Mhm.
if something is in hidden layers, we can't apply the softmax and sigmoid function, right? In hidden layers, in output layer, we can apply the softmax or sigmoid function as for the problem statement. But in hidden layers, we can't apply the softmax and sigmoid functions because the probabilities are between 0 to 1 and the learning will be very slow. That is the reason we are going to be applying the tanh problem. And so there also we are getting the problem is vanishing gradient problem, but which is the stronger gradients and the values what we are producing by this particular tanh, which is values are having the more strength. Okay, and moreover which is zero centered value, because of that one also the values having more strength. Okay, but the problem is that which is not solving the vanishing gradient problem. I would try to tell you after some time about vanishing gradient problem, or before explanation of the optimizers, then definitely I can talk about vanishing gradient problem. Okay, but to
Mhm.
overcome that one, those are just improving the sigmoid function. But industry standards, we are not using the tanh, we are not using the sigmoid functions, we are not using the softmax functions in our hidden layers because which is not solving the vanishing gradient problem. You might be feel why engine you why you are explaining this all activation functions, what really industries are using. You can explain those things also, right? Yes, of course, but we need to understand the um, different kind of activation functions and all. This activation function we are not completely neglecting. We are neglecting using in hidden layers, but we can definitely use at output layers. Okay,
Mhm.
is it clear? And so some of the activation functions which not only useful in deep learning architecture, it could help you in convolutional neural network also. That is the industry standard activation function. That is the ReLU activation function. So the ReLU activation functions, and which is the fast computation. So we can the problem
Mhm.
whatever the network we build it, and the network it can be learned in a speeder manner with help of the ReLU activation function. So the ReLU activation function, which is some kind of ramp or a linear equation we are getting, and if any value which is less than the zero, it there is no if you can apply anything, you will get either zero or else max of that particular value. There is no specific formula, and the formula is very simple. And ReLU of x is, for example, if your z value is if your z value is okay negative value. For example, if your z value is negative value, okay, if your z value is the negative value, then which is producing zero directly. For example, you are getting the z value is -2. Okay, so if you compare the -2 and the 0, which one is the max? Which one is the max? 0 is the max, right? So that is the
Mhm.
reason. If you're getting the negative z values, if you're getting the negative linear values, or step one, we are calculating weighted sum of inputs and weights, right? Okay, weighted sum of inputs and weights and plus bias, right? So those value, if it is a negative value, then the ReLU, which is straightforwarding giving like 0. There is no negative linear step one function z value. There is no z, there is no negative z values. If we have negative z values, then it will be keep 0. If you're getting the positive z value, then that z value only we are getting. So max of 0 and z. So that is the reason we are getting this particular straight line actually. Okay. And if your z values are negative values, then we are getting the zeros. If your z values are positive numbers, then you are getting the corresponding positive value only. Okay. So this is the industry standard, but it is also not useful because if when you are getting the negative values and which the network is not learning anything because straightly it is producing 0. If in the neuron output is 0, then next neurons definitely it won't learn anything, right? Are you getting my point? So
Mm.
just imagine you applied the ReLU activation function on this particular hidden neuron, and unfortunately, the weighted sum is negative value. You received it. So definitely this hidden neuron which is producing the 0. Okay, then this 0 and multiplied with this weight, definitely it is also 0, right? And if 0 is given to the neuron, then this neuron it won't learn anything, right? Okay, there is a problem here, and there could be some kind of neurons is automatically dead. Dead neuron means which is not learning anything. Got it?
Mm. Okay.
The output neuron which becomes 0, then which is not learning anything, right? Okay, so
But
to
we can't determine the value, right? We can't determine the value should not come to zero, right?
yeah, that is the reason, we are applying the different kind of activation function. We are failing. See, scientists, what they were doing actually, they were doing various research and they were creating this many activation functions. We are not using
Mm-hmm.
those all activation functions right away. We are using only few activation functions only now. But
Mm.
initially they were started using sigmoid and they failing. They were doing a lot of research and they were implemented and they were not getting that huge results. Then they went to tanh function. There also where they were failing some of the actions, and they went to softmax function, and they feel that it could definitely help for the binary sorry, multi classification. Okay, sigmoid and tanh it could help us for binary classification. But what about hidden layers issue? So in a hidden layers, we can start using ReLU activation function. But in ReLU activation function, some of the neurons are becoming 0. Even it has some data, but it is producing 0, right? So that is
Okay.
the reason. Don't use the ReLU activation function. Then they started implementing one more activation function, that is Liku ReLU. Okay, Liku ReLU. What is the activation function name? See. Mhm. So if in 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 relay activation function, some of the neurons are dead automatically. So if we are getting the negative values, and we can multiply with 0.00 some value, some less than the one. Okay, so that is the situation. If you're getting the negative values, then it could be this kind of equations, not something like straight line. It may be bend over here because we are multiplying with some smaller value. If in case for any number, if you are multiplying with a smaller number, then automatically that number it could be a smaller, right? I mean, if any number you can multiply with a less than the one, then automatically the magnitude it becomes reduce. So because of that one, even if we are receiving negative values, at least the activation function it never be dead. It can be learn something. Okay, that kind of actions it could be having in ReLU. In ReLU, it is a fast computation, and we can solving the vanishing gradient problem. And but the problem is that there could be some kind of dying ReLU. Dying ReLU means neuron stuck at 0. There might be a chance of neuron it could be stuck at 0. That is the reason we are applying the ReLU Liku ReLU activation function. In Liku relay activation function, it is of formula is, it is same like a ReLU activation function, but liquid is something like that. You can see, if in case, if your z value or your x value is more than the 0, then you will be getting that z value only. If in case, if your z value is less than the negative value, then it could be 0.01x. Okay, so that is where no, liquid will help you to, instead of dying your neurons. And there could be small gradients even for negative values, so that which is reducing the dead neurons. So with help of the liquid relu, which is improves the gradient flow for negative activations as well. Okay, those are the different kind of things. It could help you on this all activation functions. We can use it in your neural network. If you know this activation function, you can start building your own network. But don't worry about this strategies and all, and we can have the hyperparameter tuning, and we can try multiple ways to, and you will finalize the best neural network also. Okay, and to finalize your best neural network, for that one, hyperparameter tuning will help you. Those things will learn in upcoming sessions also. Hmm? Yeah, so these are the different activation functions are there. So what we do tomorrow, we can try to be implement this activation function using Python programming language. Okay,
Yeah, that
and we
helps actually.
yeah,
Mm.
chalo then. Thanks for your time, and let's meet in a deep learning session at tomorrow same time. And if anybody want to learn Python data types, then you can come for the same link in the next 2 minutes. Thanks for your time. Bye.
Thank you. Bye.